Okay, and the second speaker for this afternoon session is Dr. Thobani Gambu. He's a senior lecturer in the Chemical Engineering Department at UCT. And he's going to talk to us today about understanding the catalytic activity of molybdenum carbide surfaces, what we can learn from surface mobility of reaction intermediates.
Thank you very much for this opportunity. And I realize this is probably the last talk before the closing remarks. And so basically I'm between you and your families. I'll try and make it a little bit more boring so that you get some excitement when you get home. Yes, yeah, and thanks to the ChPC for accepting my abstract. So I had sent an abstract dealing with discussing the catalytic process happening on molybdenum carbide surfaces, and I will spend some of the time on that, and I spent very little time on discussing the current research that's happening in our group. Oh yes, yeah. So yeah, I'm from UCT and the Department of Chemical Engineering, and I worked mostly during my PhD with Professor Eric van Steen. And having left for 2 years to do a postdoc, I came back and rejoined the department as well. And where I currently work again, I still continue to work on some of my research project with Professor van Steen, also because he has the money, of course, and he's also funding my trip to also come and talk to you today. Okay. So as I said, my talk will look at understanding the catalytic activity of alpha molybdenum carbide surfaces, and with a special focus on I will try to highlight the importance of surface mobility of reaction intermediates in terms of kinetics. So the talk will generally follow this outline here. So I'll talk a little bit about Professor van Steen's group, which I worked under, give a background on the systems we work with, why we need ChPC and HPC resources, as well as look at the core focus of the abstract, which was the reaction of molybdenum carbide surfaces. I'll then look at some summary and conclusion remarks with an outlook of what we hope to do in the future based on the preliminary results we have. So just maybe to highlight this, the initial work I started during my my postdoc, where I looked at one of the surfaces, and I found it quite interesting following some experimental work which suggested very high activity at very low temperatures in terms of water gas shift reaction, which is used to convert CO and water to CO2 and hydrogen, and this is mainly applied in hydrogen fuel cell for on-site production of hydrogen. So as I have stated, we fall under the Department of Chemical Engineering at UCT, as well as the institute, which I am part of, is Catalysis Institute, and is composed of three main research centers. Within it, it's Catalysis Center. That's basically everyone who does catalysis research, as well as HISA Catalysis and C-Change. These are nationally funded research initiatives looking at excellence or competency in catalysis, as well as in hydrogen fuel cell. That's the competency center. And the department looks more like this. It's not really a nice picture. The picture of the university looks much better than this. So as I have stated, our research group has these members who are currently working active on ChPC. Professor van Steen is the current research leader, PI on the main project. I also work here, but we also have other PhD students who are currently working. Here, Tracy and Pia are currently working. Tracy's a lecturer as well as finishing up her PhD, and Pia works for Sasol, and at the same time starting his PhD. So the general trend is we have chemical problems that we would like to solve, and I think I'm not going to go in more detail here because I believe that the audience here actually understands all these. But what we try to do is basically combine both the synthesis of catalytic materials as well as modeling. So in the modeling case, we look both at the reaction of reaction intermediates and the interaction with the surface, but as well as trying to model the macrokinetic dynamics to understand what are the rates as well as what are the rate limiting steps to better inform our catalyst design approaches. So again, I brought this slide back. It's more of a cartoon version of what you saw before, but generally we are interested in understanding the conversion and as well as selectivity of our reactants and products as they go over a reactor where in this case we have catalysts and we have different types of reactor configurations, and chemical engineers in this room will know. And on these, in these reactors, we basically have a packing of say pellets or extrudates where we have the active catalytic material. But if we zoom in closer, we have surfaces where in the case of metals, you may have direct interaction of gaseous molecules with your surface going via multiple reaction intermediates towards products which also have to dissolve. All of this happens under some environmental conditions. As stated, there are 3 projects which are currently active on the ChPC, and I've listed here the main one which we work with under is this lateral interactions on surfaces. And the reason why we are interested in this is because general literature normally looks at adsorption of molecules on surfaces without considering the fact that some of these molecules will interact with each other repulsively, sometimes attractively, and that can have significant implications for the kinetics, as well from how we predict them, but as well as in terms of how we then decide to modify the catalyst materials. There's also other research looking at material side. This is with Riyad Mohammed, who is an electrolyzer unit, as well as this is a relatively newer project that I asked to be registered, where I am interested in looking at the effects of dynamic catalysis, basically trying to model responsive types of substrates, which we can use in catalysis and try and drive reactions based on dynamics. So the general problems we're interested in, obviously, is carbon dioxide conversion to useful fuels, methane conversion as well to liquid products, methanol and formaldehyde. There's a lot of interesting experimental work in this case. And again, as a result of some of the really interesting results that have been observed from the experimental side in terms of selectivity towards formaldehyde in a single step process, as well as activity have been possible because of the work being done, which was done under the lateral interactions project, which has been registered with ChPC for a while now. I also have some work where we look at Fischer-Tropsch systems, some advanced materials. This is the project with HISA, where we are trying to understand the properties of metal oxides, as well as here with the Asterix, my intended research area. Now, the reason why we need ChPC processes, resources, is because most of the analysis we do require understanding the interaction, which is absorption of reaction intermediates on the surface reactions. So I'm really happy that the previous speaker actually talked about transition states. This is basically where we need to figure out these transition states, and there might be multiple transition states, which if we want to get accurate models, we need to kind of to capture, as well as taking all that information putting it in a macrokinetic model. So for that, we also need to understand the vibrational frequencies of the reaction intermediates and transition states so that we can do some thermal corrections. Generally, the number of jobs that we require is dependent on the number of intermediates that we capture, and this is dependent on the complexity of the reaction system we look at. If you think of Fischer-Tropsch process, that number is ridiculously large, which obviously we can't do on our standard computers. Furthermore, the number of reactions also increases as a function of the number of reaction intermediates. And I just conservatively put here 2 reaction transition state search calculations, basically for every reaction that we have. And as well as we need to do dimer analysis, so to optimize the transition states. as well as look at the vibration analysis for this last part here. So in general, for the two reactions of interest, which is like here, the reverse water gas shift here. So if we want to utilize CO2, for example, to make sustainable fuels, we can consider a reaction that goes via water gas shift, reverse water gas shift first to convert CO2 to CO, which is later converted via the typical Fischer-Tropsch process. And for this case, the simple model will have 6 reactions and 6 intermediates. And you can add 2 here if you want to consider the effects of water and hydroxyl species. And this leads to about 72 jobs that we need to do. And these jobs obviously of multiple atom systems. So they take time, of course. And if we want to do something as simple as CO2 methanation here, we have about 21 intermediates and in excess of 20 reactions. And that goes to way over 204 jobs. But this is again on a single surface. In my PhD, we looked at the effect of cooperation between types of different surfaces via diffusion. And we saw that is also quite an important aspect of this. So if you wanted to truly understand the kinetic processes, you may need to consider multiple surfaces to capture that cooperative behavior. Just like the last statement here, clearly we can't do all this research without ChPC. So our typical jobs at ChPC makes use of between 2 to 4 nodes, depending on the type of calculation we're doing. So transition states versus geometry optimization calculations have different requirements. We use VASP code. We use the available polarization options within VASP. So polarizing over bands as well as polarizing over decay points. We also, before we start big projects, we do benchmarking, or we try to figure out what are the reasonable computational settings for that particular system. And and I've spoken about the resources. So my current work that I'm actually looking at now is the application of molybdenum carbide as a catalyst in CO2 hydrogenation, as well as methane activation here. And this is part of this talk, as well as modified perovskite materials. This is again with a collaboration with someone in our Catalysis Institute who's doing experimental work. They have some interesting results there, and they would like to understand how these modifiers are affecting their supports. The other bit is, again, ferroelectric materials, which is part of my project of interest here. I'll talk about molybdenum carbide systems. Generally, for this project, we use VASP, PBE functional, these other settings here. We've set NCore to 12 and about 2 nodes for the individual job. And this is more or less the amount of time it takes to run these calculations. So what we have for molybdenum carbide is we find that this type of surface, which is a 100 termination, is more stable, as well as this surface, which is a 111 phase set, is also relevant under reaction conditions. So just to revisit what I've spoken about here, we generally are interested in the conversion of products as well as selectivity. And we can solve this for a typical system like this in a plug flow reactor using an equation of this form. And for microkinetic modeling, we can get this omega value here. And this omega value depends on a reaction rate, which is different for reaction steps in our reaction mechanism. And here I've highlighted this green because the effects of lateral interactions as well as mobility of reaction intermediates affects this probability here of having the required pairs next to each other to actually have elementary reaction steps taking place. Again, this is the thermodynamic aspect of this. The rate constant we're calculating using transition state theory with the activation energy here, as well as the entropy. Again, all this information is available from DFT calculations we conduct within the ChPC. So just going back to the actual main projects that I've worked on here, which is CO2 hydrogenation. And I've highlighted here adsorption energy of different reaction intermediates, which are relevant for this process. As you can see here, basically on both the 100 surface and 111 surface, the interaction of CO2 with the surface is quite strong. And this, if you compare this to something like copper, for example, or if you compare it with nickel, where the physisorped structure of this molecule is more stable with about 20 or under 20 kilojoules per mole, so that would be 0.2 EV. These surfaces are highly reactive towards CO2, which is why they are actually interesting as materials, either to do the first reverse water gas shift process or to actually do the actual hydrogenation reaction. And again, experimentally, they have been applied as well. At least different types of crystallographic structures. And again, I've included other species here. In particular, you can see that the interaction of these intermediates varies differently, significantly depending on the surface we're looking at. And in reality, these particles are available and they may expose all these different types of surfaces. And it's important or useful to understand how they behave. So just going through, I've shown you the reaction intermediates, but I haven't shown you exactly how they actually, you get to them. So typically what we look at for this case, which is conversion between CO2 and CO, we have here, and maybe if I go back, we have here CO and hydrogen, in this case, 1 to 3 hydrogen atoms, depending on the reaction. For reverse water gas shift, you only need 1, but for the hydrogenation reactions, you obviously need more than 1, depending on the products you're trying to target. And these are some of the products that you can produce, of course. So we start with CO2, and this is it's a lot of animation here, but CO2 can directly dissociate. For it to dissociate, it will require a vacant site next to it on the surface, and that produces an oxygen. And it can also go via by the hydrogenated routes by first hydrogenating it with an adsorbed hydrogen to form a COH intermediate. And the COH intermediate can dissociate, forming an OH as well as a CO. So this cycle obviously can occur, but there are the elementary steps which haven't been considered here. Now, once we've gone through the cycle, we obviously have to deal with the oxygen that's produced as well, which is an important part of the reaction. So here you have oxygen, which can be hydrogenated to OH, and OH further hydrogenated to water. Additionally, you can couple 2 OH species to make water and O. So just from the energetics perspective, I really do apologize in terms of the faults for the reactions. But what you have there is CO2 dissociation here, with quite here what you see basically are activation energies for the different elementary steps, which are shown via this process here, and they range between they're around 1.2 electron volts, and there are some steps which are much lower. What I want to highlight here is, instead of going via the direct pathway towards CO, going via this pathway where we use water to hydrogenate CO2, forming a COH and OH, and dissociate it. This has a significantly lower activation barrier than the direct routes. Furthermore, you can see that comparing the blue and the black bars, you can see that there's a big variation between the reactivity over different surfaces. Again, I have indicated that water is also so I've also indicated that water removal or oxygen removal is also an important step. Here, again, you can see that depending on the surface, you get different reaction energetics, which have an impact, of course, on the kinetics, but as well as that for some of the surface, it's much easier here. Again, this is OH coupling here. So you have OH plus OH, which forms water. So the reverse of this process is a much easier step of removing oxygen than the direct hydrogenation process here. Okay, so if you look at this barrier here, which is a direct process, which generates an O, and compare it with the reverse of this reaction here, which, yeah, it's a little bit fainter here, but you can't see. You can see that the actual activation energy barriers are slightly different. Now, of course, once you've converted CO2 to CO, you can then convert that CO via dissociation of the carbon-oxygen bond to carbon on the surface, CH, CH2, CH3, and CH4. And this process can also be done by using an OH instead of an H, as well as a water intermediate instead of the two. And all these have different activation barriers, which then affects, of course, the kinetics. So have okay, it's taking a while, but then again, you can see like significant differences between the different surfaces as well. But you can also see very high activation barriers for some of the steps here. And this is around 2 EV here. And you can see which step of on the methanation pathway, which one is more demanding. So for example, the 111 surface, which is the black bar here, is unlikely to is less likely to make a CH4. So if you look at this barrier here, this is CH3 plus CH to CH4. Compare that to the 100 surface, which has about 1 EV in terms of activation energy so 1 EV, but 1 EV compared to 1.7 electron volts, that's a big difference, especially kinetically. So I've spoken just mainly about the reactions on the surface, and this reaction generates reaction intermediates, which obviously are sort of, well, so for each reaction, you would need, of course, to get the required intermediates to be co-adsorbed next to each other before a reaction can take place. And regardless of how fast the individual reaction steps, if diffusion of these reaction intermediates to find their corresponding pairs is slower, that process will be limited by that effect. So we try to understand this, let's calculate it for our system here. We see that for the here the 1-on-1 surface of molybdenum carbide, the activation barriers are much lower. Now these are lower than in platinum case, which is again quite interesting and promising. However, on the more stable 100 surface, these activation barriers for hydrogen or oxygen, even OH, are far larger than the largest barrier for over the platinum surface. And this again does indicate that despite the lower barriers in some of the, especially on the 100 surface, which we saw for methanation, if we can't get the reaction intermediates co-adsorbed next to each other, the rates will not proceed as we expect just from plain DFT calculation, reaction activation, transition state calculations. Now, we would like to obviously incorporate this into a microkinetic model, considering, of course, the effects of lateral interactions, as well as, so depending on the types of lateral interactions, as well as the severity of these lateral interactions, the mean field models, which we use, might be applicable or not applicable. And we'll try and see whether this has an impact in our modeling at a later stage. Now, so I guess we try to understand why the diffusion of, so generally speaking in catalysis over metal surfaces, it's not a diffusion of reaction intermediate that is a problem. The problem is generally the coupling of reaction intermediates to make other intermediates and later products, and then desorption of those products, which has higher barriers. However, in this case, as I've shown here, we saw that on the molybdenum carbide, the 001 phase set, diffusion has higher barriers than sort of expected or normal in metallic surface. So we're trying to understand here why this was the case. And we see here, if we compare, again, very small font here, if you compare here the magnitude of the charge transfer from the initial state. So if we have oxygen, which normally adsorb on one side, diffusing to the next side, if you look at the charge difference on the oxygen adsorbate basically between these two states, and that's that difference here, the magnitude of the difference here is plotted on the x-axis, and it's correlated against the diffusion barrier which the process goes over. So we're still trying to figure out why And once we know that, of course, if there are significant charge transfer if a significant charge transfer equates to a higher barrier, then by modifying so if we look at bulk modification of the molybdenum carbide, we could potentially influence electronic structure of the carbon on which the oxygen and hydrogen adsorb on, and thereby influencing the activation barrier. So just in summary, we've looked at CO2 activation, which is quite facile on both surfaces. However, there's strong adsorption of some reaction intermediates such as oxygen, which makes it difficult to later remove here. And we see also in terms of pathways that the OH coupling is important. And then again, reactant mobility may be problematic kinetically. And this is again the case for the 100 surface, which is we don't see for the 111 surface. So in terms of outlook, as I've indicated, we're considering bulk modification of molybdenum carbide systems to influence electronic structure of sites, thereby lowering the diffusion barriers of the reaction intermediates. But as well as we may consider surface modification. This has been observed in systems where they atomically deposit platinum clusters and atoms to small clusters on these surfaces, and this tends to alleviate or have a much more positive catalytic impact. Yes, I know this has been long, so I'd like to thank you for sitting through this presentation, and to thank the ChPC for the resources which have been used to do the bulk majority of this work. As indicated, our preliminary work was done using the Flemish supercomputer in Ghent, and some of the test calculations are done using our local smaller clustered university. I would like to also thank Professor Van Steen for paying the money, as well as the NRF for funding, of making those funds available, of course, and you for your attention, and my chair for.
Thank you very much, Thobani, for an excellent presentation. Do we have any questions? Yeah.
Thanks very much, Thobani. Really, really interesting, exciting work this. I'm just wondering, so in your workflow at the moment, you're specifying certain reaction pathways, and then you're testing them as to see whether or not which ones are more favorable. So is there any way to almost maybe in more, when you have maybe reaction systems with more complex reactants, I mean, is there a way to almost automatically build up the mechanism just by specifying the intermediates and then testing all the different combinations, or does it just get too computationally expensive?
Thank you very much for your interesting question. I think that will be very useful because it will reduce the number of jobs you need to do, which means you can look at more surfaces and you can do more complex analyses. However, even the two things we need to consider, the types of reaction intermediates that you're likely to form, because that will obviously influence whether other reactions are important. And in terms of that would depend strongly on the activation barriers. Or say, for example, if you have a CO, if you ask whether you will have an OH or an O, would depend whether CO actually first dissociates or hydrogenates. But also, there are obviously some thermodynamic implications on that. The other factor that we need to consider is that sometimes I think for a long time when people looked at for example, oxygen reduction reaction on platinum, they will look at direct hydrogenation. So they take O and they add hydrogen, and they add hydrogen to the OH and they make water, and then water dissociates. Okay, they could have also the O2 forming OH and then dissociation of that, or going via peroxide, hydrogen peroxide intermediate. But it took a bit of time to get to a point where people considered, can OH and OH coupling lead to water, or the reverse of that reaction lead to a much better pathway? So I think while it's useful in reducing the size of your system, you may run a risk of missing some of these finer details, because once you understand this, for example, not for oxygen interaction reaction, but for more complex and bigger reactions such as Fischer-Tropsch, then you can then start realizing, barring, of course, the water effect on the stability of the catalyst, you may realize that adding water does facilitate the reaction because it's better at reducing the CO, for example, than hydrogen on the surface. And as a result, if you exclude it from the get-go, you may not see that information and you may not run your reactor differently. In this case, of course, it doesn't work because then your catalyst sinters and deactivates as a result of water. So, but in other systems where this is not an issue, you may miss those opportunities.
Okay, thank you very much, Thobani. If I can just give you a small token of appreciation. Thank you so much. Thank you to everybody who attended the session and to both of the speakers. And then I just invite you all now to please attend the final keynote closing ceremony, which will be in the Diamond Auditorium. Thank you very much.